As you might have guessed, I'm Greek, originally Greek, and I was born in the island of Crete, which is very close to here. And last summer, when our Prime Minister came to Israel, he said that his visit was late by 25 years. And I must say I feel the same way. And I'm very pleased that I was invited here to meet you all and collaborate with scientists from Israel. Today I'm going to talk about something very specific about the application of satellite data to exposure assessment and health effects studies. And at Harvard we have a small group of people that they work on this issue, and two of them, Alexandra Chatnovsky and Itai Klug, they are postdoctoral fellows who were originally funded by the EHF and came to Harvard, and they were very productive. And I hope when they come back to Israel, they will use their skills to pursue research in exposure assessment and environmental epidemiology. As you know, we have monitoring networks that they measure concentrations in different points for regulatory purposes and for health effect studies and epidemiological studies. And of course, we cannot measure everywhere. And of course, in some cases, we cannot measure every day. So there is always the issue about exposure uncertainties, exposure error, and also we have to deal with that when we do epidemiological studies. And these days, over the last 10 years, scientists have tried to use satellite data to get a better idea about exposures. And specifically, the aerosol optical depth is one of the parameters provided by satellites. And it measures the abundance of particles in the atmosphere. And scientists, they have tried to establish relationships between fine particulates and aerosol optical depth. And I must say, these studies, they show some relationship. However, they have showed that the relationship is AOD is a moderate predictor of PM2.5, and for this reason, scientists, including myself, we try to use other covariates like meteorological variables, land use data to improve this relationship. However, I don't think we have been very successful, although if you don't have real ground data, it's good to use the AODs. And about a couple of years ago, 2 or 3 years ago, we thought that it might not be, the AOD might not be as useful to predict concentrations over time. Like if you are here and you try to predict the concentrations, you might not be able to get really strong associations between AOD and PM2.5. However, you might be able to fill up, these are sites, monitoring sites, to fill up the space. In other words, if you have a network with many sites, these are the northeastern United States, then you can fuse the ground data with satellite data and develop study the spatial patterns of pollution. And that's the base of my presentation today, and I will talk about how to calibrate aerosol optical depth data to be able to get solid, strong relationships between AOD and PM2.5. And then satellites, they don't read every day. Especially where I come from, the United States, we have snow, we have clouds, and we have retrievals only for a small fraction of the year. So how can we predict concentrations for the days we don't have satellite data? And finally, as I said, I will discuss some applications. So the first part, I will talk about the calibration method, which is actually the base of our studies. And for this paper, we use data for 1 year for the states of Vermont, Massachusetts, Connecticut. And we measure PM2.5. We took the data from the EPA monitors. We had about 26 EPA sites here. And then we use MODIS data of a 10 by 10 kilometer resolution. And specifically, we use the Terra data. And I'm not going to go through the mathematics, but the concept here is that most of the studies, they assume that there is a constant relationship between AOD and PM2.5. Like if you have a year of data, you assume that there is a linear relationship, you have an intercept and one slope. In our case, as I said, we assume that that relationship changes every day because you might have snow on the ground, the vertical distribution of aerosols changes from time to time, the composition changes, the relative humidity changes. So all these really parameters changes, they influence the relationship between AOD and PM2.5. So we let the relationship to vary by day. And to do that, without becoming very technical, we use mixed effects models, which allow for this variability. And for data, PMI, J, I is the site of one of the 26 sites, and J is the day. We use the AOD at the corresponding to that site grid cell at a day J. And this is a site-specific coefficient. So when we do that, we get, like everybody, a slope and intercept for the entire study, which is a fixed effect. But also we found that our hypothesis that this relation changes from day to day was true. And actually there was significant relation changes in the, both alpha and beta, the intercept and the slope. That indicates that it's necessary to calibrate the data. So here are the results, which I think they are pretty good. We were able to predict concentrations which were very similar to the measured. And as you can see, the R square is 0.92, and the slope is close to 1, and the small intercept. And here we take the correlations between a specific site and the AOD, the corresponding AOD at that site. And you can see the R squares between the sites, and for the different sites is very high. And here is that if we assume that there is a constant relationship throughout the study, you can see the R square is much less. So definitely there is an improvement here. So now we have a model that we can predict over space concentrations during retrieval days. What do we do for the non-retrieval days? Can we use the spatial information we get during the retrieval days to predict the spatial distribution during the non-retrieval days? And yes, we can do that. And to prove that, we did an additional study, a second study, where we took data from between 2000 and 2008. Now we have 69 EPA monitors. We use the MODIS data. And we have here about 582 grid cells of 10 by 10 kilometer within the study domain. And again, for every day, we calibrate the data to predict PM2.5. And then, without getting too technical, we take the entire data set, all the 69 sites throughout the entire period, and we do a cluster analysis. We don't touch the AODs. And for this cluster analysis, we identify 9 clusters which correspond to distinct spatial patterns which correspond to distinct meteorological conditions. Okay? So for each of these clusters now, we have similar spatial variability for the monitoring sites. And for each cluster, we have retrieval and non-retrieval days. So we develop the surface, mapping the surface, and then for the retrieval days, and we use the same mathematics, the same statistics to predict for the non-retrieval days. And very briefly, here are the entire data set. and we developed the clusters, and here are the AOD data. We merge them, and finally we can predict for the entire area. And as I said, we identify 9 clusters. The first one was the most dominant cluster, but we had some with less days. Here are the results we obtained. These are the results for the retrieval days. You see, you get a very good agreement. And here are the results of the non-retrieval days. And it's, you know, they are not as good as the retrieval days. However, they are pretty good. And here you see the R-squares between the site and the AODs for the retrieval days and the non-retrieval days. Of course, you don't get as much, the results are not as good as the retrieval days, but however, the average R-square is over 80%. And here is the percent mean relative error for the retrieval days and the non-retrieval days. So here you can see the concentration profiles for the entire study, and you can see where the population is mostly here and a high pollution near the highways. So you have a very distinct spatial profile. Here are the results that they show the spatial profiles for the 2 of the 9 clusters. And you can see indeed that the spatial profiles are very different, and you cannot really analyze all data. You really have to separate the days to correspond them to specific meteorological conditions and air pollution conditions. So now we have a model and we have an area, and we can predict concentrations over time and space. And I want to present the second part of my presentation by presenting 2 applications to environmental epidemiology. And the first has to do with birth weight. Birth weight is one of the most important parameters that can predict the development of a child, whether it's related to respiratory problems, to the cognitive problems, cardiovascular problems. So we do pay attention to factors that they might influence the weight of a baby. So we did a study in Eastern Massachusetts. We have data on the birth. We had data on the locations where the mothers were during pregnancy. We include the mothers that they had full term, like between 37 and 44 weeks. We calculated for each mother exposures for the last month, for the last trimester, and for the entire pregnant 9 months. And we control, of course, for socioeconomic status, for just race, and here are the addresses of the mothers, the entire study, for the entire study. And here are the concentrations. So we linked to each mother to a specific grid with a specific pollution. And the results are quite interesting. We found that for a change of, this shows the grams of weight loss for each child per 10 micrograms per cubic meter increments. And for the 1 month, the last month exposure, babies that they were exposed to, on average, to 10 micrograms more, their weight was 8.8 grams less. For the last trimester, why this skip? For the last trimester, 9.2, which is more than 8.8. And if you take the total the total 9 months, this estimate is considerably higher. So the larger the window of exposure, the larger the effect. So you can see that there is a great application here where you can really link chronic exposures of 1 month or 3 months or 9 months to a specific house, and you can do an analysis. The second application I will talk has to do about hospital admissions. People going to the hospital for respiratory diseases, for cardiovascular diseases, and some for diabetes. And here we studied the total region, the New England region. We identified individuals by zip number, and we used the exposure maps we have developed here, and we link each individual to a specific concentration. And this way we can calculate daily exposures, but also we can calculate the average exposure over the period between 2008 and 10. And this actually is one of the first studies that in the same model we included both short-term exposure, the daily exposure, and long-term exposure, the 8-10 years exposure. So now we can model what is the effect of the short-term exposure and what is the effect of the long-term exposure. What's the effect if today, for instance, the particles will increase by 50 micrograms per cubic meter? And what is the effect if I live in a place which is on average 10 micrograms per cubic meter more than the regional average? And you can see here that for most of the visits, we find an increase of 0.7%, 1.83, I cannot see, 0.3, and 0.96 for increased percent per 10 micrograms per cubic meter. And this is the effect of the short-term exposure. And you can see here that for the long-term exposure, the risk is higher, as you might expect, and actually is considerably higher. So this tells us that, you know, your risk increases if you live in a more polluted area in your town or in your region. So satellite data can really provide the necessary data to study the joint effects of both chronic and acute exposures. So where are we going now? Soon we will have the 1 kilometer data from NASA. I understand also that our colleagues here, Professor Brody's group, will receive similar data at the same time, so they are as privileged as we are. And we will try to analyze, use the same models, but for 1 by 1 kilometer. And here you can see the data we have right now, that on the right-hand side, you see the spatial variability based on 10 by 10 kilometers and the spatial variability based on 1 by 1 kilometer. So you really get a tremendous resolution. And as you get a better estimate of the personal exposure, you get a less biased effects estimate. So what we find from this study is that the more accurate the exposure is, the more the effects, the higher the effects you find. Okay, so in the past, by using one monitor in each city or crude exposure models, we were underestimating the effects of air pollution. And my conclusions is that first, if we do believe that the aerosol optical depth is very important, and if you allow calibrations per day, you can really get high quality data that you can borrow information from the retrieval days in terms of the special profiles of pollution that you can use to predict concentrations during the non-retrieval days. That the third thing we learn is that if you really have a rich spatiotemporal data set, you can really do a lot of many things in epidemiology. And finally, as we move from a resolution from 10 kilometers to 3 kilometers to 1 kilometer, we're really opening up a new area of exposure assessment where, on one hand, we have refined health data. Nowadays, we have access. I understand here it's still a problem, but we have access to medical data. We have access to land use data. And on the other hand, we have very good exposure measurements, so if we can really link them and better understand the effects of pollution. So I think we have made tremendous progress over the last 5–10 years. Okay, thank you very much.